All right, today we'll be talking about energy bar charts. So like we said last week, the first thing we need to know is the first law of thermodynamics. So just remember the first law of thermodynamics. Take a second, pause the video, write down what you remember from what we talked about last week. Again, we'll be revisiting this all year long, so it's important that you know the first law of thermodynamics. It says that the total energy of a system is constant. We can't create energy, we can't destroy energy, we can only transform it from one kind to another. That's it. That's the first law of thermodynamics. What we will now start doing are energy bar charts. So this is just like what you saw in the energy skate park activity. We're just going to be drawing our own instead of having the computer make them for us. So energy bar charts, they're also called LOL charts or LOL diagrams because you can see the two bars with the circle in the middle make it look like an LOL. We can use these to show what different types of energy look like. So if you want in your notes, you can draw in just the blank example of what an LOL diagram looks like or an energy bar chart. When we draw these, they have several rules. So these are the steps we want to follow when we are making them and looking at them. First up, we need to identify our system. So like we talked about last week, system, that's just the things that have energy that we care about. We are going to write that in the circle, so that goes in the O. Then we want to identify where Eg, our gravitational energy, equals 0. So this is kind of like we're setting sea level for the problem. A good way to do it is just look at the lowest point that an object goes to during the problem, and we're going to say that is equal to like sea level or an elevation of 0. That's where gravitational energy is the lowest. Then we identify the initial energies present. So this will be, it'll either say on the problem like initial or position A, something like that. And these energies, they are going to go in the first L on the left. Then we do the same thing for the final energies. They go in the bar on the bar graph on the right. So this will say final position or position B, something like that. We want to make sure we obey the first law of thermodynamics. So that's just initial energy equals final energy. And then finally, we write our energy equation. So this tells us what kind of energy did we have at the start and what kind of energy do we have at the end, and we just write that in math form. So we'll see what that looks like in a second. When we're looking at pictures, when we're looking at setups, you'll see these things in the diagram. So if it says like position A and position B, that's just initial and final respectively. You might also see a little I or a little F for initial and final. V means velocity, so that's just how fast it's going. We'll learn more about that in a future unit. Y is the height, so like it comes from y-axis, like if you think back to math class. And then if you see a couple lines behind an object, that just means it's moving. So here, if we look at this example, so like our skateboarder down here, he's moving because he has the lines behind him. Y equals 0, that means his height is 0. Vi, initial velocity, is greater than 0, moving. If we look at Bf, velocity is less than the initial velocity, so this means he's still moving, but he's going greater than 0, he's off the ground. So you can use the picture. We'll often write something next to it so you can also interpret, or so you can read the description. For a total, that's a good total number, but like if you did it with 3 or 5, that would be fine, but we just need to have the same amount of energy at the start that we do at the end. We want to remember the different energy types. So remember, kinetic is Ek, gravitational potential energy is Eg, spring or elastic potential energy is Es, electrical energy is EEL, chemical energy is Echem, and then whenever we have energy that seems to disappear, remember that is like dissipated energy or thermal energy. So we call that E-dis, or we can also call it E-thermal. And if you look at all these, so instead of writing out the word kinetic or gravitational potential each time, that's what these symbols are for. So EK, kinetic, EG, gravitational. You can use those instead of writing out the whole word. That'll make things a little faster. To identify the types of energies that are present, we want to ask ourselves the following questions. So we look at our system, looking inside of that system, so that just means looking at the objects that we're actually talking about in this problem. We want to ask ourselves first, is the object moving? If the object is moving, we say it has kinetic energy. Then we want to ask, is the object above the ground at any point? If it is, it has gravitational energy. Is the object elastic or springy? If it is, then we have spring energy. Can the object burn? We use that for E-chemical, and that's only relevant if it's going to be used later. So like sometimes an object like, yeah, it can burn, or it can burn, but we're just not going to be using it in that problem. Is electricity moving something? That would be EEL for electrical energy. And then is there friction, or does energy seem to disappear like we can't account for it? That's where we have thermal energy or dissipated energy. So now we'll get to see what that looks like in action. Here we have a car, and it tells us a spring is being used to launch a car, and then at the end the spring has sprung and the purple car is moving along the ground. So our system includes the spring, the car, and the ground. So remember the system, we write that in the O. And when we do this, we look at the start. Our car is up against the spring. It's not moving, so no kinetic energy. It's on the ground, so no gravitational energy. Hey, there's a spring, and it is compressed, so there's going to be some spring energy. And then, is there anything that can burn? I guess, yeah, the car can burn, but it's not actively being burned during this problem, so we don't care about that. And then we look at the end. Now the spring has sprung, so no more spring energy. The car is moving, so there's kinetic energy. It's on the ground, so no gravitational energy. And we just go through the questions again. So when we do that, we see at the start, like I said, spring energy. At the end, kinetic energy. And in the O, we write our system, spring, car, and ground. So we're just writing down what it is we're looking at the energy of. Energy equation, this is what it looks like. We just say what kind of energy did we have at the start equals what kind of energy did we have at the end. This is a reminder of the first law of thermodynamics, that our spring energy at the start has to be equal to our kinetic energy at the end. And if you look at our bars, notice how we gave it 4 blocks here, or this bar is 4 divisions high. At the end, we have the same total amount of energy, 4 divisions. So just remember the first law of thermodynamics. If we look at the second example, in the second example, the person is holding the books, then they're going to drop the books. So we'll say at the end, the books are about to hit the ground. This is something we will do frequently. So about to hit the ground means it's like a millimeter off the ground. So we can basically say they're on the ground, but they're still moving. So if we were to draw our LOL diagram for this one, we would want to ask ourselves the questions again. So are the books moving at the start? Nope, the person's just holding them. Are they above the ground? Yes, so that means there's going to be some gravitational energy. Are there any springs involved, chemicals, anything like that? Nope, not this time. So it's just gravitational energy at the start. At the end, the books have converted their gravitational energy because now they're about to hit the ground. So no more gravitational energy. We're just on kinetic energy because the books are moving. So our LOL diagram should look like that. EG equals EK. Notice again, same total amount at the start. So we have 4 total blocks here, 4 total blocks at the end. In our third problem, here we have a skateboarder rolling down a walkway, and they're going to jump off this ramp. So our system here includes the skateboarder and the ramp. So at the start, skateboarder moving, it tells us initial velocity is bigger than 0, so that means they're moving. Y equals 0, that means they're on the ground. At the end, they're going slower. VF is less than VI, and they're off the ground. Y is greater than 0. So still moving, off the ground, just not moving as fast. In this one, we ask ourselves the questions again. For the picture in part A, are they moving? Yes, there's going to be some kinetic energy. Are they off the ground? Nope, no gravitational energy. Is there a spring? Are there chemicals? Is there electricity? No to all of those, so it's just kinetic energy at the start. At the end, we look and we see the skateboarder off the ground, so there's going to be some gravitational energy. We know they're moving, so there's going to be some kinetic energy. So now we have to decide how much of each of those energies are there. So if we look at our example here, We just say at the start, all kinetic energy, so we just made it 4 blocks high, and then at the end, we say there's some EK and some EG. If we go back to the beginning of these notes, we said these are qualitative, so that means we don't have quantities. So all I know for sure, because it tells me right here, is that the final velocity is less than the initial velocity. So I just know EK has to go down. I don't know if it's 1 bar, 2 bars, 3 bars, any of those would be fine. It just has some kinetic energy because it's moving, and less than at the start because it's not moving as fast. So the rest just goes into EG. So alternatively, I could do 2 and 2, or I could do 3 blocks of EK and only 1 of EG. But notice again, the first law of thermodynamics, however much energy we have at the start, we need that same amount of energy at the end. So 4 blocks at the start, I have 1 plus 1, 2, 3 more for a total of 4 blocks of energy at the end. And our energy equation here, kinetic energy at the start, becomes kinetic energy at the end, and also some gravitational energy. So this is another reminder of the first law of thermodynamics.